Well, thank you very much, Tim, for a nice introduction. It's amazing to come back here and see how much you've done for hepatitis B and for biotech in this country. This is a great pleasure for me to be here. I was very surprised, but very honored to receive this award. And I just want to say there's a long road to the cure of hepatitis B. And why I put that title in this, I really believe when we started to work on the antivirals that maybe we had a cure for hepatitis B, not just a treatment to suppress the virus, but maybe a cure. And it turned out to be much more difficult to cure. But I believe we will get there in time. Let me just say that we're not moving.
You're about to slide? Oh, no.
No, I don't know why. Oh, it's moving now. Thank you. So this is going to be some historical recollection of some of the contributions. And some of the slides are older slides, technologies, but that's how it all evolved. I'm going to talk a little bit about hepatitis C and the animal model, and then the importance of moving from discovery to translation. When I started this work, I got to say that there was a lot of people in universities who felt if you worked with industry, that was you were contaminated by industry. And I got to say that, in fact, we had our president of the university was asked, because we got some money from Glaxo to help this, one of the first collaborations between university and industry. And somebody asked if this wasn't tainted money that was coming in to do research in the university. I always remember his response. He said, yes, you're right, it is tainted. There tain't enough of it. So anyways, and I'll finish off just with a brief on the Li Kai-shing Institute. Of course, it's such an honor to have a prize named after Barack Blumberg, and who discovered the hepatitis B virus, Nobel laureate. He also was a Canada Gairdner winner, and such a contribution to so many areas of science. And his major discovery was the hepatitis B virus, as you know, and that changed the world of hepatitis. Let me just say that persistent viral infections as a clinician in infectious diseases, I've got to say that when I started practicing, hepatitis B was not in the infectious disease world. It was all in the gastroenterologists and hepatologists. But I think I was the first clinician in Canada to start seeing hepatitis B patients. And I realized it was such a problem. And following a few of those patients, I built up a practice in hepatitis B. And at the time, most infectious disease people thought it was crazy. But let me just say, persistent viral infections are very important. Chronic hepatitis B, nearly 300 million people estimated even last year, 3.7% of the world's population, and about 820,000 deaths a year. Chronic hepatitis C is 70 to 100 million people in the world, and about 500,000 people a year die from chronic hep C. And HIV, 30 to 40 million, and it's about 680,000 people still dying from HIV worldwide, estimated. Of course, hepatitis B causes liver fibrosis, cirrhosis, and hepatocellular carcinoma. And as I said, I think it's 820,000 estimated to die from hepatitis B. I want to say that when I finished my infectious disease training, I wanted to do a postdoc in virology. And thought maybe the best place to go to do that would be with Bob Purcell. And I contacted him. He was very generous with his advice, and we had a nice conversation. And I wanted to work on hepatitis B. And he said, well, you know, there's no cell culture system, and that's going to be tough. And he said, you need access to a chimpanzee colony. are you going to go back to Canada? I said, probably would. And I said, without chimpanzees, it's going to be hard to work if you don't have a chimp colony. And so I took that advice to heart, and I thought it was the right advice at that time. And I changed my career, I was still interested in multiple sclerosis. And there was a role of paramyxovirus at that time in the thought of multiple sclerosis. So I joined Erling Norby's lab in Karolinska Institute for my postdoc. And Erling was on the Nobel Committee. And this was 1975, 76. And as it turns out, my wife and I got tickets to attend the Nobel ceremony in 1976. And of course, at that ceremony, who was to win but Blumberg that year. So I got to meet him in Stockholm, got to meet him in their lab, came through and toured the lab and talked to him, and then of course attended the ceremony, and it was a wonderful experience for us. So I came back and I set up my lab and working in MS and had grants for that, but was teaching a graduate course. And I was asked to review persistent viral infections in that graduate course. And I came across this paper and realized this was, to me, is the most important paper that I ever read. It was a critical paper in the hepatitis field because through the work of Jesse Summers and Bill Mason, we had now the replication models for hepatitis C. This is a primitive example, but it just simply shows this was the only DNA virus going through an RNA intermediate back to DNA. And it was also interesting that I switched my research lab and went into hepatitis B. And the similarities between hepatitis B and HIV and the replication. So when I started my work, there was still not very good cell culture systems. And the only animal model for the human was hepatitis B, was the chimp, as Bob Purcell had told me. But there were other viruses coming up, the Peking duck and the woodchucks. And I simply thought when I read that paper, could we not use the duck model to come up with surrogate as a surrogate for human hepatitis B? And if we found good drugs that would inhibit the duck virus, would it inhibit the human virus? And I called Jesse Summers and asked him if he was interested in working on this. He said, not really, I'm a basic scientist. He said, has anybody talked to you about using duck models? I said, no. I said, do you mind if I have someone come down and learn the duck model at Fox Chase? And I sent a postdoc down, Satoru Suzuki, and we brought it back to the lab and set up the cell culture system for the duck hepatocytes. And key to this was Professor Morris Robbins, who was a professor of chemistry at the University of Alberta, but an outstanding nucleoside chemist, nucleotides, and he was the first to synthesize DDA and DDG. The purine analogs were tougher to synthesize in those days, but Morris and his Robbins paper had first synthesized the dideoxys. In fact, he sent some of these to Sanger for some of the Sanger rapid enzyme sequencing. Morris supplied some of those key nucleosides. Morris was at the University of Alberta, moved to Brigham Young, but we continued to collaborate throughout this progress. And the thing was, I needed ducks. And I got to say that first I got them from a farm we got from Jesse Summers, where they got the ducks. It was from a farm here in Pennsylvania. And the older couple were raising the ducks. And we were having breakfast one morning at home. And they called and they said their farm had a fire the night before. And you'd have to find another source for the ducks. Of course, I touched bases with Patricia Marion, who was at Stanford, and she said there's a place in Gonzales, California, that this guy will send them to you. I called him and he said, yes, I'll package them very carefully and I'll send them to you. They'll arrive in Edmonton. And so we tried a couple dozen eggs and then up to 5 dozen eggs, and he sent this big box. And I got a call from the post office. And they said, we have a box here with your name on it, and it's sticky, and it's got a problem. Would you come down and look after it? So I went down to the post office. I can still remember it was noon. Most people sitting in the little side room lunch. So I quietly went in and took my box, emptied it. It was a mess. Out of the 60 eggs in it, I think I had 12 or 13 that weren't broken, but the rest were all broken. It had gone through a conveyor belt and dropped about 10 or 12 feet. Anyways, I cleaned that up. And I took the eggs back to my lab. And I no sooner got there than I got a phone call from Agriculture Canada saying, "What are you doing? You're not allowed to be importing these eggs this way." So I said, "Return them immediately." So I started to return them, and I thought, I need these eggs to continue the work. So I took some large chicken eggs and returned some chicken eggs to Agriculture Canada. And they were quite satisfied with that and never bothered me again, but they did say I couldn't import them. And I hatched those out, and we raised them on my parents' farm. In the beginning, I didn't have a lot of money to do this work. As you know, in those days, you did clinical trials, and there was little money from clinical trials that I began raising the ducks on my parents' farm. My parents were old. This is their 50th anniversary of the farm. And my dad thought I was crazy, but I was raising ducks. We never raised ducks on the farm ever. And so we did, and we set it up. And across the top here, you can see 20 days in culture, we had high levels of hepatitis B. The darker the dots, the more hepatitis B in these dot plots. But dideoxythymidine didn't seem to make any difference. This is 20 days and 20 days. DDC had some effect, but not much. ERA A, another compound that had been used, and we had used a little bit of Hep B, wasn't very good, but it had some inhibition. But what was really surprising was to see DDG down here. There was more than 10,000 times more effective than DDC or DDT. So we began to wonder, why is that these are so much more effective than the other dideoxynucleosides? And what we presumed was that, or worked out, was that the primer protein that triggers the DNA synthesis always has a deoxyguanosine as the first nucleotide. And if you incorporate dideoxys further down, they would be proofread out. Even though there's no clear proofreading of the hepatitis B virus, we thought they would be proofread out. But DDG, the binding to the primer protein, was clearly different. And this linkage to a tyrosine primer protein area really did stop the DNA synthesis. I can just say that the polymerase, and when we looked at the polymerase labeled with DDG, dideoxyguanosine, you just saw a little labeling that it did bind. The other dideoxys did not give this signal, and they were labeled. And if you put in just DDGTP labeled, of course, you got this signal plus the growing nucleotide. So we did publish the selective inhibition of duck hepatitis by 2,3 dideoxyguanosine triphosphates or prodrugs of it, but we worked with Morris. I want to say that we took these dideoxyguanosines, a prodrug of it, prodrug of this, and converted to DDG, treated 12 animals, ducks, with placebo at A. B was the DDG prodrug, and this was DDA. And you can see that after 1 week, 2 weeks, or 3 weeks, we saw the blood clear in the ducks, and we were very excited that we thought this was a real treatment for hepatitis B, at least the duck virus. And this led to a collaboration. We went down to Research Triangle Park, Morris Robbins and I. We met with Glaxo or GSK at that time. I tried some other companies at the time, but GSK was the most interesting for us. And we ended up getting a contract from them and worked with GSK for quite a number of years. And in working with GSK, we used the duck models to screen a lot of compounds. We did over 160 the first year and about 400 total. But one of the ones that we looked at was used in duplicate here, the number 22 and number 19. We had unmarked lots that seemed to inhibit, and this was the 3TC, or the minus enantiomer of 3TC, or lamivudine. And it was being developed for HIV at this time, and we knew that it was going to become it became the lead product for us in this collaboration. Let me say it was synthesized by Bernard Berlot and McGill. There was a spin-off company, Biochem Pharma, and Glaxo Wellcome had licensed lamivudine from Biochem Pharma, and we asked for testing it because of the similarities between HIV and hepatitis B, who could be tested against our duck model. And we did, went back to the ducks, and surprisingly, and this is ours, we used large doses of lamivudine. 3 ducks received lamivudine and 3 received placebo. And you can see that the half-life in this was something in the range of about 7 to 8 hours, how fast the virus actually disappeared with the high doses of lamivudine. And we then wanted to know if it worked in the human virus. And working with Ron Keeney from Glaxo at that time, found a chimpanzee colony in New Iberia, Louisiana, where they had done the vaccine studies, including some of the animals got placebos and some got the real vaccine. And there were a number of these mothers or chimps that were carriers of hepatitis B. And we found 3 young chimps that were chronic carriers, vertically transmitted from their mothers. And this is just one of them. And this was using hepatitis B DNA and just looking at the hepatitis B DNA with low doses of lamivudine. We did this study by just every 2 weeks, increasing the dose to see if we could find a dose that would inhibit human hepatitis B. And you can see that in the duck, we saw this great inhibition. And it worked and showed that a hepatitis B human virus also was inhibited dramatically by this. So we took these results back to the lab and did the analysis, and we're delighted to see how rapidly this disappeared. Mechanism of action with lamivudine was different because it is a pyrimidine. But I want to say that DNA polymerization is reversible in the presence of pyrophosphate. And when you look at the hepatitis B replicating cores, 3,200 nucleic acids in the hepatitis B replication. And it's a very small volume and tends to hold the pyrophosphate in it. Pyrophosphate did cause the reversal of the incorporation of DDC, DDG, or DDA. DDG never really got incorporated, but DDA, DDT, and DDC would get incorporated, but would clear out, but 3TC did not. And we know that it was being incorporated and that it was not being proofread out as the other nucleotides. So it was unique in that way. And we published the pyrophosphorylalysis of the hepatitis B polymerase in the replicating cores could inhibit the mechanism of action of 3TC in duck virus was published. Of course, this had cleared for work with HIV. So we did a study in Europe, the United States, and Canada on some patients with chronic hepatitis B using different doses. And we found that anything over 100 milligrams per day in these patients caused very significant, after 30 days, very large drops of hepatitis B DNA. And there are many studies that have been done. I'm not going to go through those, but that was our original study. This is a study in China just showing that people who were treated had better survival than the control group. These were males that were carrying hepatitis B chronically, and the treated group and the control group getting hepatocellular carcinoma. So there was clear differences, and there was a big study in China. It was done by Lee, and that study was terminated, designed for a 5-year study, terminated after 3 years because of the significance that was shown with treatment of hepatitis B in preventing cirrhosis and cancer. One of the things that happened was liver transplants had been shut down in many places, including our place, if you had hepatitis B, because new transplanted livers got infected right away and developed a very rapidly progressive disease, sclerosing not sclerosing cholangitis, but very aggressive hepatitis B in the transplanted liver. And so we got permission from our ethics committee locally, because we had a patient who needed to go for a liver transplant, and this is before it was fully licensed. And so we found that the first, I think one of the first, or if not the first patient in the world to receive lamivudine pre and post-transplant. Patient was in ICU and actually got a liver flown in from San Francisco at that time. And Norm Kniedemann, our liver surgeon, did the transplant, and we gave this patient lamivudine for a few days. He was in ICU, and then after we continued post-transplantation with lamivudine and H-big. And I just want to say, this is Lorne, who did the transplant, and I worked with the mouse model. And this is Morris Robbins and I to see this first patient. This patient recovered and did very well, and the explant had lots of evidence in brown of hepatitis B, but the transplanted liver, this biopsy was taken about 8 months later, still had no sign of hepatitis B in it. By the way, this patient went 9 years perfectly healthy. Then the transplant team had something new on it, and the patient saw that person, and they said, "Why are you still on lamivudine? It's 9 years ago. Can't be doing anything now. Stop the lamivudine," unfortunately. And I didn't know about that. And that was in April, and the patient came in fulminant hepatitis B in July and died of his hepatitis. But while he was on lamivudine, he had done very well. So we had done a few more, and lamivudine antiviral therapy has become standard if these patients have to go to transplant. The other question we had is, didn't know at this time, is whether treatment was the cirrhosis, was the fibrosis reversible or not. And this was a biopsy that was taken in one of our patients, and across the top you see a very cirrhotic biopsy. And this is in C, is 2 years after he was on lamivudine. Biopsies in this patient showed remarkable increase or improvement in his fibrosis. And hepatitis B patients going for surgery often had to go on to antiviral therapy for their transplant. And even some of those with severe cirrhosis reverse their disease and become compensated. And about 70% in these earlier papers suggested about 70% could be prevent the transplant and reverse the fibrosis. So that was another important aspect. We always had, I had some concerns about lamivudine and developing resistance. And one of the people in my lab, we did site-specific mutagenesis and mutated the virus with thymine to a valine in the binding site. And you can see the virus didn't replicate as well, but in the presence of 3TC, you wiped out the virus in cell culture, but with this mutation, it remained almost the same as the untreated levels. And we published this, that duck hepatitis virus with the mutations in the polymerase, and we reported this with genetically engineering lamivudine resistance serves as a cautionary note of what could occur with lamivudine as monotherapy and prolonged treatment. Well, that didn't take very long before it was demonstrated that lamivudine characterized some of the mutants of lamivudine resistance. And although it was the first drug licensed, Galactus had collected them, and we published the lamivudine mutants. Let me say, lamivudine was licensed in 1998, and then other drugs came along, and today, entecavir and tenofovir are drugs that have really very low, or tenofovir low resistance. and they have become the drugs of choice in the treatment of hepatitis B over lamivudine. But lamivudine was the first. The whole goal of therapy is to normalize the liver transaminases, get the level of hepatitis B DNA down to undetectable levels, improve the histology, and prevent progression in cirrhosis or hepatoma. Let me just say that we would love to be curing and get rid of all of this. However, this is in Canada, lamivudine was licensed in 1998 as Heptavir. And the problem with all of this is that these drugs do suppress the virus levels. They do improve, it meets all those goals, but in the replication of Jesse Summers and Bill Mason work, they have shown that there's a covalent and closed circular DNA in the nucleus of the infected cells. Antivirals act out here, but they do not destroy the CCC DNA. And our long road, what we thought was going to be a cure, is a treatment, and a cure, getting rid of the CCC DNA, is still something we're all trying to do. A lot of people are working on. And I think that I can say that there are a number of approaches all around this site here that are looking at how you might be able to get rid of the CCC DNA. And a lot of work has been done, I think, in some of these areas here by Tim and others, and Sin Urban, and a number of people are coming up with ways that we might be able to do this. We're just beginning another collaboration with Michael Gale on looking at some of his stimulators immune response in combination, and see if that can make a difference using the mouse model. So I just want to say that briefly on hepatitis C, after we did the work on this and saw the value of the duck model and what we did, working with Lorne and an excellent graduate student, David Mercer, we began working on hepatitis C and wanted to see if we could develop an animal model for hepatitis C, because we saw the value of the duck model. This is Lorne again, and David Mercer was graduate student. He's now a transplant surgeon in Omaha, Nebraska, but he did an excellent job on this, working on this model. It was taking immune skid mice and putting hepatocytes into the spleen. They moved into the liver very quickly, and you could see human albumin being produced shortly after they were transplanted, but it petered out, it disappeared. I was on the supervising committee with David, and I said, David, I think what we need to do is find some way to disadvantage the mouse hepatocytes that are still out competing the human hepatocytes. So I come from a farm, and if you don't spray the weeds, you're not going to get a crop. And we need to see how we can give an advantage to the human hepatocytes. And there was papers, Grinster had done some work and published on knocking down endogenous hepatocytes with the transgene that we picked up the urokinase, and we bred that into our mice. This was a transgene that had under the albumin promoter, but 4 copies of urokinase, and we modified this, put it in, and we could then take to these mice that were skid gauge mice. They had no immune system, and they had disadvantaged, their hepatocytes were going to die, and we put in human cells that didn't have the transgene, and the human cells would get into the liver and replace the mouse hepatocytes. And this is just a picture of human hepatocytes in a mouse liver replacing the sick mouse cells that are pale, and the human hepatocytes are nice and red and healthy. We can get mice that are transplanted up to over 90% of their liver is humanized, and we used this to try to infect. At this time, there was no animal model for hepatitis C other than chimps. I would say that we expanded. I showed you how the albumin disappeared. Now this is 4, 5, 6 weeks. In the presence of the transgene, you can see how the human hepatocytes expanded and human albumin increased. So that was the key to getting this to work. But we infected them with hepatitis C. And I got to say, in the first experiment we did, we had 22 mice. I was hoping to find most of them would be infected with hepatitis C. But in science, only one animal out of all of these actually had hepatitis C. And what we did is we analyzed that mouse and found that it was homozygous for the transgene, and other mice were hemizygous. We converted our colony over to producing almost all homozygous mice for the transgene, infected them with hepatitis C, and we got levels of virus that remained constant in these mice of hepatitis C and went out. Now this mouse model is used for hepatitis B, as Tim has mentioned, and the nice thing is it has all the components of the hepatitis B replication, infection, and cccDNA. So it's a good model to study some of the things we wanted. We passed this hepatitis C from mouse to mouse in order to get it published in Nature Medicine. It was published in 2001 as the first non-primate animal model that supported hepatitis C replication. This is the first mouse that we had infected with hepatitis C, and I should have said that we incorporated a company, KMT Hepatech, Caneedum, Mercer, Tyrrell. We had put in AV, we just wanted to call it Hepatech Technologies, but HEPA Filters complained that it was too close to their name. So we put the initials in front, and we had, by 2003, we had good contracts with Chiron. That's how I met Michael Houghton and Weiss, and we had signed a lot of NDAs because people wanted to test compounds in these mice. We got a contract from the NIH as a site for testing hepatitis C compounds in the animal model. And 2007, we couldn't keep up. We licensed to Phoenix Bio, and Phoenix Bio was doing most of their work in Asia. They wanted to come into North America, and we permitted that. And the NIH contract was extended to hepatitis B as well. And Phoenix Bio did a public offering and raised money and purchased KMT Hepatech from us in 2017. But this model, the Phoenix Bio mouse, is really the KMT mouse that we licensed. Now, I did want to say that hepatitis B was a major issue in China, as everyone knows. And we worked on the first oral antiviral for this, Morris Robbins at the U of A. And we knew that Mr. Li Kai-shing was involved in husky oil in Alberta, and heavy investment in husky oil successfully. And that he is a philanthropist. He's set up at least 15 institutes around the world. And we approached him about getting the hepatitis B or getting the Li Kai-shing Institute at the U of A. This unusual structure here is Shantou University Medical School. It's 9 stories high. It's designed by the same architect that did the bird's nest in the Olympics. And Mr. Li hired him to build a new medical school in Shantou. This just gives you a better picture of it. 9 stories high. It's got all of the departments in these various aspects. These are people in front of it to get an idea of how big it really is. And it is a remarkable facility. I've been to it a couple of times. So we approached Mr. Li, and he agreed. They agreed to establish an institute of virology at the University of Alberta, and we had the official announcement on April the 23rd, 2010. Critical to that was we had in Canada what they called Canada Excellence Research Chairs. And these were an opportunity to recruit somebody to your institution who would give it an extra boost. And we're very fortunate that Michael Houghton agreed to be a Canada Excellence Research Chair to provide $10 million over 7 years of research support to do this. And Michael came to the University of Alberta. Mr. Li Kai-shing also insisted, and I just put in very bold here, that the research must benefit patients. He didn't want us just to have discovery research. He wanted to see it being translate it into benefit patients wherever we could. And we set up not only the Li Kai-shing Institute, but in it, the Applied Virology Institute. And Michael is the director of the Applied Virology Institute, and I direct the Li Kai-shing Institute Discovery. And this is the Li Kai-shing Applied Virology Institute is located in this building. It's on the 7th floor. And the Li Kai-shing Institute of Virology is located on the 6th floor in an adjacent building. The government didn't want to, and the government of Alberta put in a lot of money to this for the commercialization, and they did not want to see it being used in the discovery research, just the way they were. So they wanted these two separate in location a bit. And of course, having Michael here was a very important part for us, because Michael was awarded the Nobel Prize along with Harvey Alter and Charlie Rice in 2020 for the discovery of the hepatitis C virus. And I just want to say that that was huge for Canada to win a Nobel Prize in physiology or medicine, because we only had, in this category, we only had Banting and Best in 1923, were the only Canadians to win a Nobel Prize in medicine or physiology. So it was nearly 100 years since we had won this, and having Michael win it was very important. So the viral research that I've been involved in was, we used the duck model, primary hepatocytes, to discover that the purine nucleoside analogs were much more potent than the pyrimidine analogs. And of course, tenofovir, these are more purine-like derivatives now. And I think the key is binding to the primer protein and stopping the synthesis directly, and no further synthesis once they bind to the primer protein. We demonstrated lamivudine as the first oral antiviral for hepatitis B. Just wanted to say that Ray Shinalzi and the group had worked on this as well, and we have patents and the dates of our patents, and Ray's at the time the date of discovery versus the date of patents, and the date of discovery preceded our date of patent filing. So in the United States, Ray's got done extremely well, as everybody knows, with those patents. We developed the first non-primate animal to support hepatitis C replication, and it's also excellent for hepatitis B, and is continued to be used a lot. And in 2010, we established the Li Kai-shing Institute of Virology. We now have 49 people in the institute as investigators, and there's about 180 people that work in the institute between the two, integrated into the department. And the recruitment of Michael Houghton was critically important for Canada, as it was subsequently Nobel Prize in medicine and physiology. So I just want to acknowledge my research group that worked on the hepatitis B in the 1990s, and I'm not going to go through names here, but some were key people that really did some outstanding work. Bonita Lee did a lot of the work in the cell cultures, and, but I won't go through and name all of the different people. And this was in 2013 when we were working on the mouse model and getting into some hepatitis C work, and we still continued some hepatitis B. So key financial support came from the Canadian Institutes for Medical Research, from the Alberta Heritage Foundation for Medical Research, from Glaxo Canada, continued to support us until the drug was licensed in 1998 from 1987. And Western Economic Development is another Canadian that helped build the facilities for the Applied Virology Institute. And of course, the funding we got from the Li Kai-shing Foundation to establish the, it's an endowment we have of $25 million that helps us. And the Alberta government double matched it at $50 million to give us the money to expand the institutes. And I just want to say a tremendous thank you to both Tim and Joan, who have done so much for hepatitis B in this world, not just in the United States, but the Hepatitis B Foundation. And what they have done has been remarkable. And what we see here is remarkable as a legacy. And I know that Tim is going to be retiring soon, and Joan. So I just want to thank both of you again for all you've done for the world of hepatitis B. That is really remarkable, and very, very honored to receive this award from the Blumberg Institute and the Hepatitis B Foundation. And want to thank my wife, who's here at the back of the room. 52 years of marriage. This is the early days. But she's been a tremendous support throughout all of this work. And in fact, when we have the ducks out at the University Farm, she would go out there and help change and clean up the ducks in the early days. So I will stop at that point to say thank you very much. It's a great pleasure to be here, and I'd be happy to answer any questions that people might have. Thank you.
Thank you very much. A great talk. And